Right, so displacement, velocity, and acceleration. So for those of you who are saying you didn't understand why it was meters per second, you're about to understand it.
That's acceleration.
Yes, it is.
Physics.
Okay, so starting with displacement. It is the specification of an object's location from a certain point. So if we say we got our little axis, and that's the point O. When you say moving along this line, you're going away from O. So up to here would be like x equals 5. And down here could be like x equals -7. It's no different from a normal number line. So when you're moving, say we've got a particle that starts at O, here, O. That's why I'm saying O, because it's not 0, it's O, point O. Okay, and it's moving towards 5. If we kind of graph that over time, so we're going to have displacement over time. We've got point O. You can treat it like a 0. It's essentially 0. We want to go up to 5 here. That'll be going down as well. If we're going from 0 up to 5 over a certain amount of time, we'll say that it's moving in a constant rate. Which way is it going to go?
Positive, so the bottom left.
Yeah, up. Yeah, so it's going to go kind of up to 5. Right, now, if at 5, it stops and then goes back the other way towards -7. Oh, we'll say for now towards 0, back towards 0. Where's the line going to go?
Down.
Back down, yeah. And then if it keeps going and it goes to -7, it's obviously just going to keep going down like that. Right? If it then stops at -7, goes back to 0, goes like that. So anytime you're moving to the right, what's the gradient going to be?
Positive.
Positive.
So the distance is here.
Oh, is that a distance, not displacement?
No, that's
This is displacement.
new.
What are you asking? You're okay?
There's no such
Say,
Kev will tell you that.
I absolutely hate the term negative. No, decelerate. Because it's a negative.
wait, did you say there's not negative displacement?
Yeah.
So you're saying there shouldn't be a -7?
No, but there's a difference because this distance is like
Displacement always
here.
shows positive number.
Like if you move from here, here, and here, the displacement is only there, but the distance is here and back. So there's
Right.
no negative displacement. It's just how far
How far it is from the point.
A.
Yeah.
Well, I'm right. So
Yeah, no, that's good. Right, so yeah, if it's moving to the right, the gradient should be positive. If it's moving to the left, the gradient should be negative. Okay. Let's just, so we've got the example. A particle starts at t equals 0 and moves to the right. At t equals 5, the particle stops and moves left. So the following positions are observed. T equals 0, x equals 0. So when you're starting, your particle is at position 0. After 5, we'll say seconds, then it has moved to the position 4.5, we'll say centimeters away from the starting point. And at t equals 7 seconds, it is now 3.1 centimeters away from the starting point, but to the left. So we're asked to graph that. We don't assume a constant rate of change though, because particle speeds up and slows down.
So, but if that was like, so the bottom one was t equals 10 seconds.
Yep.
And x was equal to 9. You'd say that's a constant.
10 to 9. What do you mean?
So if it was like t, so if it was bottom
Oh, okay.
7,
Yep.
you change that to a t equals 10, and x would be equal.
Not necessarily, because you could have something like, so you got 0, 0, 5 there and there, right? But it could go like that.
That's acceleration.
So not necessarily.
Yeah.
It definitely looks like it would be a straight line, but not always. But good question. Okay, so we'll just do some rough 1, 2, 3, 4, 5,
So T is
6.
time, right?
T is time, yes. Because when we're graphing it, we're doing displacement over time. Oh, sorry, displacement usually in meters. I was saying centimeters before. Usually in meters. So it's meters per second. Yeah. 1, 2, 3, 4, 5. 1, 2, 3, 4. Okay, so our particle starts at 0, 0. Then it moves to t equals 5 and x equals 4.5. So that's about there. And then it moves to t7 and x equals negative 3.1. So about there. Now we're not given any other information, so we don't know too much about how it's moving in between those points, but as long as you join them up, that should be okay. So let's say you can do it like a rough estimate, assuming that it's not moving when it's at t equals 0, it's got to speed up. So it should start off slow and kind of come up faster. So even if we wanted to make it more obvious, say it starts off slow, speeds up, speeds up, speeds up, slows down when it gets to 5, stops when it gets to 5, starts off slow, speeds up, speeds up, speeds up. Does that make sense? Because if the particle is not moving at 0, it's got to speed up. When it approaches t equals 5, it's got to slow down. So when it gets to t equals 5, it can stop and then speed up again the other way.
Miss.
Yeah.
So when
That's
it
a
says
second.
x equals negative 3.1.
Yep.
That's not where it hits the x-axis, is it? Or are we not worried about where it hits the x-axis? Like the t.
This x is not talking about the x-axis. The t-axis is the x-axis. The x is the displacement. So you could call this one the x-axis. The x-axis in this case is the y-axis. Yeah. So because your displacement is in meters and your time is in seconds, if we look for displacement over time, it is meters per second. So you can jot that down as a little note. Displacement is meters per second. All right, velocity. Velocity is the change in displacement over time. Wait, what? Oh, hold on. No. Let's go back. Oh, wait, we can't. No, displacement's not meters per second. Displacement is just meters.
Meters.
Because we're just meters away from something.
Doesn't it have a direction, miss?
Yes, it does.
Yeah.
Velocity, magnitude, and direction. Is that right?
You get more into physics that I don't know too much about.
Okay.
Sure, you're right.
You're right? Yeah.
But we don't write the direction down in the map. Like, we wouldn't say 20 meters north.
No.
20 or like 20.
20 meters away from the starting point or from a certain point. Yeah, sorry. Displacement is in just meters. I was getting ahead of myself. Velocity is in meters per second.
Right.
Because we take the displacement over time. So it's meters per second. Yeah. Okay, so velocity is the change in displacement over the change in time. Now, from the graph we saw before, displacement was on the y-axis and time was on the x-axis. So if we're looking for change in displacement, it's also known as the change in y. So that's the change in y. Time was on the x-axis, so we get change in time. Sorry, change in x, which is also known as y2 minus y1 over x2 minus x1. Ah. Right, y2 minus y1 just means the change in y, and x2 minus x1 is the change in x. So actually, also we'll add this in, change in displacement is in meters, and change in time is in seconds, in meters per second. So if we want to graph the velocity, all we're doing is looking at the instantaneous rate of change, or the gradient, of our displacement graph, and graphing the gradient over time. Sounds tricky. It kind of is. So, yeah, we'll say to graph velocity, graph the gradient of displacement over time. So our first graph, we'll just draw it quickly again, looked something like that, roughly. So that was displacement in meters, and this was time in seconds. So now if we want to do this, this was the displacement graph. Now we want to do the velocity graph. This one's going to be velocity in meters per second, and this one is time in seconds. Okay, looking at the start of this graph, what's the gradient right at that point? 0. Yeah, it'd be about there. So we're going to graph 0 at 0 seconds. I think that one was about 5. So 4, 3, 2, 1, 2, 3. Oh, those ones were a little bit different. It's about that. Okay, good. Now we'll go to 5. So that was 5 here. Up here, what's the gradient? Yeah. Remember, draw a tangent line?
Yeah.
The gradient's 0. So we'll go 1, 2, 3, 4, 5, 6, 7. the gradient down here, 1, 2, 3, 4, at t equals 5 is also going to be 0. Let's try about halfway. So let's go to 3. Now, roughly, what's going to be the gradient at that point?
We have to draw a tangent line.
Yeah. Probably better if you look at the one on the sheet, because this one's really rough on the screen. So we draw a tangent line, so it'd probably be like around there. Draw. Can anyone estimate what it might be? Yeah, I'd probably make the line come down to the 1. It's like that line would probably come down to the 1. And I think on here that went up to about a 3. 2, 1. So like you make a triangle, rise over run, 3 over 3. Oh wait, sorry, 3 over 2. 2, because you go from 1 to 3. At this point, it's estimation.
Yeah,
In chapter 19, you'll work out how to find the exact instantaneous gradient. Yeah, so here we've got 3 over 2. So we're going to say about 1.5. So 1, 2. We're going to go at t equals 3. We're going to plot it at about 1.5. What about, we'll go with 6. So say roughly about there. What's an estimate? First of all, is it going to be positive or negative?
Negative.
Yeah, it's going to be negative. So it'll be somewhere down here. Just whereabouts. It's pretty steep. Any estimations? I'd say it's a little bit steeper than the t equals 3 one. So we'll go say about 2.5, negative 2.5. Yeah. All right, so t equals 6. Let's go down to about negative 2.5. So if you want to get super accurate, you would do that at every single point along the line. But of course, that would never end because there's infinite number of points along the line. But this is just a rough estimate. So we'll say the gradient, the graph of the gradient of displacement is, probably something like that.
More data.
well, yeah, well, it doesn't.
So basically all you want to do is just look at the gradient at certain points and plot them on another graph. Knowing that if you've got a positive gradient, it'll be in the top section, and if you've got a negative gradient, it'll be down the bottom. So all you're doing is graphing gradient over time. Gradient versus time.
Is there like an amount, like how many points we should usually pick, like 3 or 4? Or...
No, it depends on the question. Enough to get the basic shape of it. Yeah. Okay, next one. Acceleration. Yeah, because acceleration is the change in velocity over time in meters per second or meters per second squared. So acceleration is the change in velocity over time, and we know that the change in velocity is the change in displacement over the change in time. And the change in displacement is meters, change in time is seconds, change in time is seconds, so we get meters per second per second.
Life changing.
No?
No.
Just a fraction of...
Right. change in velocity over change in time. We know that velocity is meters per second, and if we take that over time, we get meters per second per second. Do we understand how we get from meters per second to meters per second squared? You know, that's just like a maths fraction thing. So if you got meters per second and you divide that by seconds over 1, you times it, you flip the second one, and you get s times s is s squared. So that's how you get the second squared. Yeah. Sorry? No, it's always good to know how they get that. Don't just accept things as they are.
I don't accept it.
Oh, sorry. Before we get to that, if you flip the page, you'll see that I've got the other graph I forgot to go through. So I don't think we can skip back to it. But back in doing velocity, I'll just draw it now. We had one that looked like up, down, up. So if you're drawing that gradient over time, we'll say the gradient of this one is roughly positive, what do we do, 2. So because it's a straight line, is the gradient actually ever changing?
No.
No. So between 0 and 2 seconds, it's always 2. So that's why it would be like that. And then between 2 and 3 seconds, the gradient is always about -5. So then it'd be like that. And then between 3 and 5 seconds, the gradient is always 1. So again, it would be like that. So that's where those straight lines come from. The gradient's not changing. Yeah.
In the example, like the circles that are filled in, does that mean so that they're not inclusive of that point?
Yeah, because at that point, it doesn't really have a gradient. It has both of them. So we don't include those points. I wasn't actually too sure. The textbook just said open circle. So I just assumed because it's at that point there's like both lines intersecting. It doesn't really have one or the other gradient. Yeah. All right, let's get back to acceleration. Right, so if we're doing, ooh, that's very thick. Thin. Okay, so change in velocity over change in time, right? That one. In the previous graph, we had velocity on the y-axis and time on the x-axis. So this is actually just the change in y over the change in x. Also known as y2 minus y1 over x2 minus x1. So all you're doing again is just taking the gradient of the velocity graph and graphing that against time. It's just repeating the step again. So before, I'll try and copy it out. Time in seconds, we had velocity in meters per second, and it was 1, 2, 1, 2, 3, 4, 5, 6, 7.
No.
2, 4, 6. It was here, 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 and roughly about here. Oops. Okay, so that was roughly our velocity graph. So if you want to graph acceleration, all we're going to do is graph the gradient of that graph. So this would be acceleration in meters per second squared, and this is time. 1, 2, 3, 4, 5, 6, 7. It'll go up to about 1 and that's not gonna work. Go up to 1 and then down there. Right, so let's take a look at this graph. Let's go with this one because it's the easiest. What's the gradient at t equals 3? Great, it's 0. So t equals 3, that's going to be 0. What's the graph down here at t equals 0? Oh, be careful.
1.5.
Yeah, right. It's kind of like that. Yeah, it's I'd probably make it keep going up to about there. Make a triangle out of that. You got 1 over 2. So it's at about a half. So probably stays like that. Definitely stays like that at here. It's definitely still that. So I'd say at t equals 1, it's still about a half. It's kind of, the gradient's getting more closer and closer to 0 as you kind of approach that point there. So, you know, it's getting closer to 0. Oops. Getting down there. And then as we start going down here, it's getting more and more negative because it's getting steeper. So it's going to start going down here. We'll say at this point, what's the gradient at that point roughly? It's about there. Yeah, if we kind of keep it going, we can kind of make one there. Yeah, -1. So at t equals 5, so 4, 5, it's about there. We know that at t equals 4, it's kind of speeding up to that -1, so it'd probably be about there. And then from there on, it kind of keeps a constant gradient. So we're going to keep going kind of out that way. Because in the initial sentence, when we wrote down like t equals 0, x equals 0, t equals 5, x equals 4.5, there was nothing after the t equals 7 to show that it slowed down and went back the other way. We just assume that it keeps going that way forever. So yeah, eventually it's going to start going probably at a constant rate maybe. So yeah, that's why our acceleration would kind of flatten out over time. Yeah?
Kept graphing the gradient of graphs, like kept dividing by size. Would it eventually like straighten out to a straight line?
It's a good question. It might. You can always try it. You'd have to be pretty accurate with it though. But yeah, I'm not sure. I've never even thought of that. See if you can look it up. So yeah, are there any questions? That's the general gist of it all. Do we get the meters per second now?
Let's do calculus.
Okay.